This is going to be section 1.3, finding limits analytically. And I'll start by discussing this recurring example that I went over in the previous videos. An example is to find the limit as x approaches 1 of the function x cubed minus 1 over x minus 1. Now, section 1.2 dealt with the graphical approach and numerical approach. And when we handled this example, this is the graph. So this curve, that's f of x equals x cubed minus 1 over x minus 1. And we notice there's a hole at the point 1, 3. So the graph is not defined. F is not defined at x equals 3. Sorry, x equals 1. But the limit still exists. And recall the limit talks about the behavior of the graph when it's approaching a fixed value. Now, if we're approaching 1, 1's our fixed value, the approaching 1 from the right side, the graph's getting closer and closer to that hole. So as x approaches 1 from the right, the y-coordinate, so the graph itself, f of x, approaches the y-coordinate 3. And then similar that we approached 1 from the left side, the y-coordinates, so the actual graph f of x is still approaching that hole, which has a y-coordinate of 3. So since these were the same value of 3, so these are the same from both sides, we can go ahead and say the limit is 3. All right, that's using the graphical approach. And again, the limit's 3, but the point itself is a hole. So the graph f of x may not be defined at x equals 1, but still the limit can exist. Now the other approach is using numerical approach. In numerical approach, you just make a table of values, and then choose some values that are close to 1. So choose some x values close to 1. Since that's 1's our fixed value that we're trying to find the limit. And I usually pick 2 values to the left of 1, 2 values to the right of 1. All right, so then after you do that, you just plug the x coordinate into the function. So then for the values you pick, plug them into the function. Like for example, if I did the 0.99, our function's x cubed minus 1 over x minus 1. That's going to be 0.99 cubed minus 1 over 0.99 minus 1. which from the textbook, they rounded to 3 decimal places, approximately to 0.2970. Right, and you do that for the other ones. Okay, that's the numerical approach, and if you notice, if I approach one, I'll use be consistent. So approach one from the left, meaning that these values up top, the y coordinates of these are approaching 3. Approach one from the right, so the values that are below 1, these values are approaching the same value, 3. So they're both approaching 3. And they both appear to be approaching 3, which this isn't a certain thing. It's just based on a pattern or observing. It looks like it's going to be 3. Both sides approach what looks like could be 3. So therefore, the limit is 3. Right, and the last video dealt with several examples where we demonstrated both of these approaches. And I said in another video that we'll be using the analytical approach. So I think it might help to look at the graph first to build an intuition of what the limit's going to be. So this section deals with the analytical approach. And demonstrating for this example in particular, at first try to see if the fixed value that I'm given for the limit that it's approaching to, I try plugging it in for x. Sometimes it'll work, sometimes it doesn't work. In this case, when you plugged 1 in, you get 0 for 0, which is called an indeterminate form. So I used some algebra tricks, so some algebra technique with factoring. I use a factoring technique to simplify. And the factoring technique was difference of cubes, because I have an exponent of 3 for the variable, and it's two values. I have x cubed and then 1. And then it's the difference because of the subtraction sign. So difference of cubes is a cubed minus b cubed. Factors into a minus b times a squared plus ab plus b squared. So that's what I used in this problem in the earlier video. So this translates or simplifies into, or factors, sorry, into x minus 1 times x squared plus x plus 1 up top. And then I have the x minus 1 on the bottom, and then we cancel out common factors. And we're left with x squared plus x plus 1. And now if I plug in 1, that's 1 squared plus 1 plus 1, you get 3. All right, this is the analytical approach demonstrated. And I'll write in general how you would handle these problems analytically. All right, the first thing I did for this one is I tried just plugging in the fixed value. So all of these problems, the format's going to be limit x approaches some value c, and it's of the function f of x. And the first thing I would do, so step 1, is see if just plugging in c or whatever the fixed value is, see if that works. So first, see if plugging in x equals c works. If it does not work, meaning it doesn't give you a value that you can determine what the limit is. So if it doesn't work, try one of the following. So try for this problem, we used a factoring technique. Okay, so this will be, sorry, gotta get the screen to come over. Let's be like step 2. If it doesn't work, try factoring technique. After you factor, after canceling common factors, then try plugging in at the x equals c. Okay, so I would try factoring technique. Now, if factoring doesn't work, so if factoring doesn't work, I'm going to try what's called rationalizing. I haven't done an example yet with this, but you'll see later on. Try a rationalizing technique. So you're going to rationalize either the numerator or denominator. Then simplify. And then after simplifying, plug in x equals c. So first thing is you try plugging in x equals c, see if that works. If that doesn't work, try factoring so that you can cancel out common factors. Now, if factoring doesn't work, then try this rationalizing technique. So underline, use factoring technique, or use a rationalizing technique. Now, if factoring or rationalizing doesn't work, try using one of the special theorems that I'll write. And really, it's in our textbook. If you go on page 69, it's theorem 1.8. That's called the squeeze theorem. And then theorem 1.9. And that's called two special trig limits. All right, so this is like an approach that I'm going to do for these problems. So in general, analytical approach, again, the first step, just plug in x equals c, see if that works. If it doesn't work, try factoring. If factoring doesn't apply, try this rationalizing technique. Now, if factoring or rationalizing it should be don't work. Both of them don't work. Then I try using one of the special theorems. And it's on page 69, theorem 1.8, called a squeeze theorem, theorem 1.9, two special trig limits. And you'll see that in a second when I get to the problem. All right, so I paused the video so I could write down these examples. I wrote the strategy. Now I'm going to go into some examples, and these examples are going to be finding the following limits. And I wrote down what the example numbers are in the textbook. And these ones I'm about to do, you can actually just find the limit just by doing the first step of my strategy I wrote up, just plugging in x equals c. And so for number 5, so I'll use green for the solutions. Again, so I just try plugging in 2, and that's going to give 2 cubed, which is 8. And that's going to be our limit. That's as easy as that. You just try plugging it in. Now number 9. When I plug in -3 in for x, and I be careful because I put the x squared with parentheses, -3 in parentheses, then squared, and then plus 3 times parentheses -3. So I usually will put a parentheses around the variable when I plug in the value in for the variable. All right, so -3 squared, that's going to be 9. 3 times -3, that's -9. That's going to be 0. Now number 13. So plug in 3 in for x. So that's going to be the square root of 3 plus 8, which is the square root of 11. And I'm just going to leave it like that, leave it in exact form. Don't approximate. All right, and same premise, number 17, I plug in 2. That's 2 times 2 plus 1 on the denominator. Right, and so 2 times 2 is 4. 4 plus 1 is 5, so that's going to be 3/5. All right, so those were as straightforward as just plugging in the value that you're trying to find the limit of. And just as an aside, let's say I, like for number 13, say instead of asking for limit as x goes to 3, let's say the limit that goes to 2, x goes to 2 of the square root of x plus 8. If I plug in 2, that's going to give me a square root of 10. All right, and then that's going to be the answer for that one. There's no way I can simplify it, so let me try a different one. Let's say it was 4. So 4 plus 8, square root of 12. And you can simplify this. Right, because square root of 12, that's square root of 4 times 3. And you can take the square root of 4. Square root of 4 is 2. So that's 2 square root of 3. And this would be the answer for that one. So anytime you have radicals, you want to simplify and leave them in exact form. All right, so I'm going to go on to another example. And this example will be number 23. And change the color back to blue. All right, say I give you two functions. F of x is equal to 5 minus x. G of x is equal to x cubed. And we're going to find the following. Part A, limit x goes to 1 of f of x. Part B is going to be limit as x goes to 4 of g of x. And then part C is going to be limit as x goes to 1 of g parentheses f of x. And that's for part C, this is a composite function. And for the composite function, you're going to apply the function f of x first. And it's going to involve, so if I have the limit x goes to c of some composite function g parentheses f of x, you first focus on finding the limit as x goes to c of f of x. So it's going to be g parentheses limit goes x to c of f of x. All right, that's going to be important, I guess, rule for limits of composite functions. All right, so let me work out the problems. All right, so for part A, they want limit as x goes to 1 of f of x. I'll still try plugging in 1 in for x. So that's going to equal 5 minus 1, which gives you 4. Now for part B, so we're doing the limit as x goes to 4 of g of x, and so I just plug 4 in for x. G of x is x cubed, so that's going to be 4 cubed, which 4 cubed is 64. Now for part C, I use some different colors for this. I'll do blue for f of x, and then I'll use green for g of x. All right, so they want the limit as x goes to 1 of g of f of x. So limit x goes to 1, and it's going to be g, and then parentheses f of x. Right, and so what we do is I apply what I had starred. This is going to equal g, and then parentheses, the limit x goes to 1 of f of x. That's based on that relationship. Well, we already found limit as x goes to 1 of f of x. That was found in part A. Just to recap, so that's 5 minus x, so it'd be 5 minus 1. So limit x goes to 1 of 5 minus x. That's 4. So now I just substitute in the parentheses the value 4. All right, and then I plug 4 into the function. Well, it's x cubed, so it's going to be equal to 4 cubed. All right, so that one was using composite function relationship. Let's do an aside. Let's say, what if I asked for the limit, say x goes to 4 of, not g, f of g of x. All right, and again, I'll use different colors for f and then g. F is 5 minus x. And then g, I'll use green. That's x cubed. Well, based on the rule. So I pretty much distribute the x limit part to inside of the parentheses with g of x. So it's going to be equal to f, and then parentheses, and inside the parentheses, I'll do the limit x goes to 4 of g of x. So I essentially just bring the limit inside the parentheses. So limit of x goes to 4 of g of x. We found that earlier, but I'll just go ahead and demonstrate it again. That's limit x goes to 4 of x cubed. X cubed, that's 64. Because if you plug 4 in, that's 4 cubed. So 64. So now I'm replacing what's in parentheses with the value 64. Right, because that's what I did over here. Now I plug in 64 in for x into the function f of x. So that's going to be 5 minus x. That'll be 5 minus 64. All right, so negative 59. All right, that was just an aside, just to go over that I'm still applying the same rule that I had in asterisks right there. All right, so I'll still keep going. This time I'll do some trig function examples. So this one's going to be number 27. And all of these examples I've done so far, I've only dealt with having to do step 1 in this strategy. It worked every time that I just plugged in the fixed value, x equals c. All right, and this one's going to be limit x goes to pi over 2 of sine of x. All right, so I just plug pi over 2 in for x. And then sine of pi over 2, that's going to be 1. All right, so we should know our trigonometry. All right, so based on the unit circle, we have this point, 0, 1. That occurs at over 2 or 90 degrees, and cosine is the x-coordinate. Sine is always the y-coordinate based on our unit circle, so we should be familiar with this at this stage. Number 31 is the limit as x goes to 0 of secant 2x. So I plug in 0 in for x. So that's secant of 2 times 0. Well, 2 times 0 is 0, so that's just secant of 0. And then I see, well, what is secant of 0? So you'd have to know from trigonometry. Secant of theta is 1 over cosine of theta. That's reciprocal identity. So I could say secant of 0 is 1 over cosine of 0. And at 0, cosine is 1. That's 1 over 1. So you get 1. All right, so at the point 1 comma 0, that's at 0 degrees or 0 radians. Right, cosine is 1. All right, number 35. Limit as x goes to 3. And it's going to be tangent pi x over 4. So I just plug 3 in. That'll be limit. Sorry, the limit, I'm plugging 3 in, so it's just tangent of 3 pi over 4. And I recall that tangent of theta is sine over cosine. So I could write this as sine of 3 pi over 4 over cosine of 3 pi over 4. And that's where I would reference the unit circle, and at 3 pi over 4, sine is square root of 2 over 2. And then cosine is negative square root of 2 over 2. So the square root of 2 over 2s, they divide each other out, so you get 1, and because of the minus sign in the denominator, this turns out to be negative 1. All right, so all of the examples I've done up until this point, minus the example I was doing at the beginning of the video, you just plugged in the value. Now I'm going to do ones where you're going to use different techniques, like a factoring technique or rationalizing technique. All right, so this next example is going to be an example where I have to use some factoring technique. This example is number 49. All right, so it's x minus 4 over x squared minus 16. Now, if I tried plugging in 4, you get 4 minus 4 over 4 squared minus 16, which we know 4 squared 16, so that's 16 minus 16 on the denominator. So you get 0 over 0, right, indeterminate form. But from algebra, you can factor x squared minus 16. That's using a difference of squares formula. right? A squared minus b squared factors into a minus b times a plus b. All right, so plugging in didn't work. Now I try to see, well, can I do a factoring technique? And I can apply this difference of squares formula. So when I find the limit, I could rewrite it. So I have x minus 4 up top. The difference of squares applied to the x squared minus 16. That makes that x minus 4 times x plus 4. And the x minus 4s will divide each other out. So you're left with 1 over x plus 4. All right, and then you could plug in 4, see if that works now. Because you can't go any further with the factoring. All right, so that's 1 over 8. All right, so that's an example where you had to use a factoring technique. This next example is going to be one that involves using a rationalizing technique. All right, and this is number 55. And it's limit x goes to 0. And it's the square root of x plus 5 minus square root of 5 over x. So if I try plugging in 0, you get the square root of 0 plus 5 and then minus square root of 5 divided by 0. And that's going to be 0 over 0, which is the indeterminate form. So direct substitution doesn't work. So now I'm going to try to think of some way I can simplify this. Now I can't really factor, but anytime there's a square root involved, so the idea is I want to hopefully get rid of the square root up top. So there's no factoring that can be applied. So let me just first note that. So no factoring can be applied. Notice that the numerator has radical signs, square root signs. So notice the numerator has some radicals. And when this happens, we try to essentially get rid of the square root signs by using the rationalizing technique. Now, how am I going to rationalize? Now, what I'm going to use is sort of the reverse of difference of squares. So if I have a minus b times a plus b, that turns into a squared minus b squared. Now for our example, so we had minus square root of 5 over x. So think of it as the A portion. This is like our A minus B. This is like A, that's B, and then I have the minus sign that's in between. So I can multiply top and bottom by the conjugates, what it's called. So if you have A minus B, you change the sign, A plus B is its conjugate. In this case, we had square root of x plus 5 minus square root of 5. So its conjugate's going to be changing the sign from a minus to a plus. All right, that's the conjugate. And whatever that is, that's what I'm going to multiply top and bottom by. So I'll write in parentheses, so multiplying top and bottom by the conjugate. So square root of x plus 5 plus square root of 5, and I do that top and bottom since they were essentially multiplying it by 1. And we know it's going to turn into this a squared minus b squared thing. So in this case, our a is square root of x plus 5. So it's going to turn into square root of x plus 5 squared. And then minus b squared, or b is square root of 5. So b minus square root of 5 squared by using this relationship. And on the bottom, I'm just going to write it how you just leave it as x, and then parentheses the x squared, x plus 5 plus square root of 5. Now, when you square a square root, that gets rid of the square root. So essentially, I can say this turns into x plus 5. That square root goes away, then minus 5, the other square root goes away. And now I can simplify this by canceling out 5 and minus 5. And I got x on the numerator and denominator I can divide out. So this is why I did not distribute the x. I left it in factored form. So then that gets rid of the x up top, which leaves me with 1. Over square root of x plus 5 plus square root of 5. Now I don't have anything in the numerator that will cause me to have 0 when I plug in x. So now I just directly substitute x as 0. That's going to make this 1 over the square root of 0 plus 5 plus square root of 5. And so that means I have 2 square root of 5s. So that's 1 over 2 square root of 5. And I'll just go ahead and say I'm okay with this if you put that as the answer. You can still rationalize, meaning you can get rid of the square root in the denominator. So simplify by rationalizing again, which that just means getting rid of the square root. And so what I mean by that, so if I want to get rid of the square root of 5, I can multiply top and bottom by the square root of 5. So up top I have square root of 5 and then divided by. So square root of 5 times square root of 5 makes the square root sign go away. Essentially I have 2 times 5. So I just ignore the square root sign because I'm multiplying it with itself twice. That would be like doing square root of 5 squared. So that makes that 2 times 5, which is 10. All right, so square root of 5 over 10. All right, that's another possible answer. All right, I'm going to go over this one, recap it again. So this was one where I used rationalizing, because at first when I plug 0, I get 0 over 0 in determinate form. There's no factoring that I can do. So then I try to see, well, what else is in my toolbox? And then in the toolbox I can do rationalizing. And I usually rationalize when there's square root signs involved. And it's a technique to get rid of the square root sign. And the relationship is if you have a minus b times a plus b, that gives you a squared minus b squared, so that you want these squares to cancel out the square roots. And so I had a minus b, its conjugate is a plus b. In our case, we had square root of x plus 5 and then minus square root of 5, so its conjugate's the same thing, except it's a plus sign in the middle. A is the square root of x plus 5, b is going to be the square root of 5. And what that was, its conjugate, I multiplied top and bottom by the conjugate. So that's what I'm doing in purple. And then I'm using that relationship, well, it turns into a squared minus b squared. So that's where the square root of x plus 5 squared comes from, then minus square root of 5 squared comes from. The square roots cancel with the squares, so you can just write that as x plus 5 minus 5. And I did not distribute the x, so don't distribute until the very end if you have to. So don't distribute x. Leave as is to see if some simplifying cancels out. To see if some cancellation can happen in later steps. All right, and then after I did not distribute x, and so I just went about simplifying it more, the x plus 5 minus 5, the plus 5 and minus 5 cancel out. So you're left with x up top. Then I have x over x times the square root of x plus 5 plus square root of 5, so I can divide out, cancel out the x's. That's why I didn't distribute x. Leaves me with 1. And then now I have no variable up top to where if I plug it in, I won't get 0 in the numerator. Now I can try plugging in what the limit is, like what the value that we're approaching. In this case, it's 0. And so I plugged in 0, I get 1 over square root of 0 plus 5 plus square root of 5, which that means there's 2 square root of 5s in the denominator. And I said, I'm okay with this as your answer. But you can still simplify further. by rationalizing again. And again, rationalizing is just a technique so that the square root either doesn't appear in the denominator or doesn't appear in the numerator, whichever one I guess you want to go about it. It's just rewriting the same value. So by rationalizing, you can get rid of the square root on the denominator by multiplying top and bottom by square root of 5. So that's why I have square root of 5 times, and then the square root of 5 times itself gives me 5. So we get 2 times 5. So that's why the other answer you could have is square root of 5 over 10. Right, and so these two examples were ones where I had to use rationalizing, and then one where I had to use factoring. These other examples, you were just plugging in the values in for x. So for the next video, because I feel like this video is already long enough, I'm going to make a part 2 to this. For the next video, I'll do more examples of this rationalizing and factoring techniques. And then I'll also do one example or two where you have to use one of these special theorems. And then an example having to use one of the special theorems that I haven't talked about yet. All right, so this video I feel is long enough, so I'll end it here and then start out with some rationalizing and factoring examples in the next video. Still section 1.3.